This one's working. Very good. All right, today, 6/6/18. Shh. Hey, today's a significant day. Today is the anniversary of D-Day, which is the day in World War II that we started to take back France. It was probably one of the bloodiest days of World War II, but very significant day. We started liberating France today, 50 some odd years ago. Anyway, moving on. So, back to math, okay? So, family. So, we're going to talk today about a couple of different graphs. One is a linear function. We know what that looks like. If it's straight, it's going to be a linear, right? Quadratic, it looks like a parabola. We're going to use this formula for quadratic. Exponential. Exponential can sometimes look like quadratic. The difference is exponentials will never go back up, right? They just get smaller and smaller and smaller, okay? And the square roots look like this. And then there are no negatives on the square roots also, okay? So let's take a look at our notes. Let's do a scatter plot and say, okay, which one does it look like, okay? So example 1, okay? Create a scatter plot. So first of all, let's go ahead and graph it. As you put more weight on a spring, it goes and stretches longer and longer and longer, right? You got a spring, put a weight on a spring, and it stretches it out, right? So if we were to put in a mass of 4 kilograms, our spring would be down to 30.7 or 30.6. So I'll guesstimate it's right about there. 5 put me at 32, right about there. 6 would give me about a 33.4, right about there. 7 would be about a 34, right about there. 8 would be about a 36, maybe there. 9 would be a 37, maybe about there. 10 to 39, okay, right about there, okay? All right, so if I graph that, and I'm looking at all my different graphs, could be linear, couldn't it? Looks pretty linear, you guys agree? Might be linear, okay? So if I think it's linear, I'm going to go ahead and try and draw in my line. Okay, looks pretty linear. Okay, so I'll say, okay, it seems to be linear, right? Right. Now we could do math the hard way, and we could do the y equals mx plus b, and we could solve it, or we could let our calculator. We're going to let the calculator do it for me, right? So to let the calculator do it, let's put it into stat, right? So if I go to my calculator, right, I'm going to go ahead and hit clear. I go to stat. Remember doing this? Stat. Edit, right? Do you want me to write these steps down? Okay, stat. I'm going to edit. Curly's. Thank you. Edit. And I want to go to my list 1, list 2. So I'm going to clear out. Clear list 1, clear list 2. So clear all my lists. So I'm going to clear lists. Okay. And now what I want to do then is start putting in data points. Okay. So I'll put in my mass or kilograms. I'll put into list 1. This will be my list 1. And my length will be list 2. So I'll go 4, 5, 6, 7, 8, 9, 10, right? And we'll put in our length into list 2, 30.6, 32, 33.4, 36.2, 37.6. Now, you're way ahead of me. I like that. We're not going to graph. We want an equation. So, Tammy, I want to calculate. I'm going to say it again. I want to calculate an answer, okay? So I'm going to go back to stat again. And I'm going to calculate. Well, great question. We think it's linear, don't we? We think it's linear, so I'm going to go down to my linear reg, which is my number 4, okay? So I'm going to my linear regression, that's what it means. Enter. Now, what I have to do in my calculator, because I have an old calculator, I have to tell it where my numbers are. Well, my numbers are in list 1 and list 2. So I go list 1. So I'm going to go L1, comma L2. So I'm going to go L1, which is in blue. L1, comma, L2. The newer calculators, you don't have to do that, but the old calculators have to tell where the lists are. Soli's got a fancy calculator, so you don't have to do that. Don't do your Soli. And now I'm just going to push enter. Oh my goodness. Oh my goodness. So let's find out what I did wrong. All right, let's clear that. Find out what I did wrong. Stat, edit. Uh-oh, I see what I did wrong.
You missed a number.
I missed a number. 30. I got 30.6, 32, 33.4. I got, oh, there's my mistake. 34.8, enter. 36.2, enter. 37.6, enter. And then 39. See, the numbers had to match up, didn't they? Now they all match up. Do it again. Stat. Good thing I made a mistake, because if you made a mistake, now it's on film what I did wrong, right? Linear regression. Let's try it again. L1, comma, L2, and again, there we go. So here's my answer. I get y equals ax plus b, but they tell us a is 1.4. They tell us b is 25, and they give us this r squared and this r. Those are really good numbers, okay, but I'll explain those in a second. So my equation is y equals 1.4x plus 25. That's my equation. I'm going to highlight that. That's my equation, right? Okay. Now, these two numbers, girls, Stephanie, put the phone away. These two numbers are really good. We picked the right number. If it's 1, it means 100% of our data fits this line perfectly. If you get a number like 1 or very close to 1, you know you've picked the right line. Does that make sense? If you get a number close to 0, you're way off. You get the wrong line, okay? 0 means no correlation at all. 1 means 100% correlation. So we picked the right one. Good job. Katie?
What if we didn't have the r squared or r?
So the way you get that is to go to tests. So we're going to do, I think it's in catalog actually, so clear real quick. So Katie, we're going to go to catalog, and we're going to go to either turn it on, is it the reg line? Let me keep going. I'm going to keep going down. I got to remember, oh, diagnosis, there it is. So you want to go to turn it on and off, you go to diagnosis, on or off. So you push enter, off. I'm going to clear that because I want to turn, mine's already on, right? Okay, so go to diagnostics. I do not want mine off. I want mine on, so I'm not going to do it. But you find yours. Yours are probably off. You want to turn it on, right?
How do you turn it on?
Here, let me turn mine off. Done. Okay, I'll do it again. Go to catalog. Okay. Let me go to diagnosis. Diagnostic tests. A, B, C, D. Here it is. So diagnostics on, right? Are you there with me?
Yeah, I got
Enter. Done.
back.
Okay.
Done.
Done. So now I've got it. R will show up and R squared will show up. Okay. All right. Sound good?
Yeah.
We'll wait for Katie. We'll do example 2. That was pretty easy, wasn't it? Yeah. We actually have learned some math in here, haven't we? As painful as it's been, we have learned some. Okay. Number 2.
Got it.
So we got the diameter of the tree and we got the age. So diameter is about 1.6. So I'll estimate 1.6 and age of 2. Age of 3 and about 3.6. 1, 2, 3, 4, 5, 6, 7, 8. So 3.6 and about 3. 4, it's about 6.4. It's about here. 5 is at 10, so let's even off my, oops, what am I doing? Yeah, 10. I'm wrong.
This graph is backwards.
I am backwards.
Yeah, like the constant should be the x value, right?
Right.
That's
I.
confusing. Oh, I don't have an eraser.
That's all right. I got white out. I think I'm in the wrong spot. Yeah. Okay, age is 2 and about 1.6. 2 and about 1.6. 1.6, sorry, 1.6 is my diameter and about 2. Okay, there we go. Boom. 3.6 and about 3. Boom. 4 and about 6.4. 6.4
No,
and 4.
He switched.
no, you switched it the wrong way though, right?
No, here's my diameter. 6.4 and about 4.
But the years are the constant, so the years should be the x value, correct?
We can do it that way. We can do it that way. You want to do it that way?
Like the diameter is dependent on your age, because your age, you're gonna age no matter what, but.
It doesn't make any sense. This graph doesn't make any sense.
Okay, they want a square graph, but I would agree with you. Okay, let's just.
Oh, okay, so do it their way even though it's.
No, we'll do it. Your way actually makes more sense. We'll do age.
Yeah, okay, that's how like scientifically you graph. Okay.
I agree with you. I totally agree with you. That's why we'll change it. 100%. The book wants to do it the other way, but Claire, I totally agree with you. That's why I was even doing it wrong, because I totally agree with you. Age, we go to 1, 2, 3, 4, 5, 6, 7, 8, and then we got to get all the way to 25, so we'll go 10, 20, maybe 25. There we go. Claire, I like your idea better.
So we're gonna go with the graph, I just realized that. Maybe this is why we're not supposed to do it this way.
It's all good. So we've got an age of 2 and a diameter of 1.6. You can barely see it, right? We have an age of 3 and a diameter of 3.6. Right about there. Age of 4 and about 6. Maybe about there. Age of 5 and 10. Age of 6 and 14. Age of 7 and 19. And 25. Okay. Now it's a matter of if we want to use a quadratic or if we want to do exponential. We're going to do both. We're going to do both. But we're going to do both real easily because we're going to put this stuff in the calculator and we're going to check the R on both. And the one that gives us the best R is the one we pick. Make sense? Okay, so let's put them both in the calculator. And again, we're going to reverse this to list 1, list 2. You guys okay with that? We switch around list 1, list 2. I agree. Claire, totally agree with you. Did you get it already?
Yeah.
You're way ahead of me. I like that. So let's go to stat, right? Edit, clear, and let's put in 2, 3, 4, 5, 6, 7, 8. Okay. List 2 will go 1.6, 3.6, 6.4, 10, 14.4, 19.6, and 25.6. Okay, got it? So now it's easy. We're going to test both, and we're going to see which one gets the best R factor. Okay, so I'm going to go back to stat. Am I going too fast? So let's check it out. Okay, stat. So let's check out the quadratic first. Okay, here's my quadratic. Okay, I'm going to go L1, comma, L2. And mostly what I want to find is the R. Okay, so it gives me the R squared. Ooh, well that's, if R equals 1, I already know which one it's going to be, right? You guys agree? If R equals 1, then I'm going to use the quadratic, right? Let me check the other one just for the heck of it. Okay, so if I go back to stat, calculate, my exponentials there, L1, comma, L2. Oh, see, it's a different R, and the R is still good. My R is still a good R. It's still a really good R, but my quadratic is much better. It's 100%, right? So it's got to be quadratic. So let's go back to, these are quadratic, not the exponential. Okay, I'll go back to my stat again, calculate my quadratic L1, comma, L2. Oops, that's supposed to be a comma. Okay, so here I go. I know that A is 0.4, B is 0, and C is 0. Well, this is an easy equation. It's just going to be y equals a 0.4x squared, right? Plus 0, right? Okay, pretty easy, right? Okay. Hey, ready to turn the page? I'll wait for you, Ashley. Of course I will. So the nice thing about this very last chapter is it's stuff we've done before, right? We know all these graphs. We've looked at all these graphs. We're just going to finish up the year by looking at them again, okay?
Yes, sir.
Okay, ready to turn the page? Okay, turn the page. Okay, last one. A zoologist is monitoring the size of a herd. Okay, we got time. That makes sense, doesn't it? That should be my control variable. And buffalo, okay? So, let's see what happens. We got 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 5 is 124. 124 is about there. 6 is 150. It's about there. 785 is about, maybe about there. 8 is 213. 213 is about, maybe right about there. Maybe. Yeah, about there. 9 is 260. 1 is about, maybe there. It looks linear, doesn't it?
Yeah.
Looks pretty linear to me, okay? Looks linear, right? So, same thing. Let's check it out, okay? Okay. Clear. You're already ahead of me. I like that. Stat. Edit. Clear. And clear. 5, 6, 7, 8, 9, 10, and 124, 150, 185, 213, 261, and 322. Okay, right? Thumbs up so far? Calculate. Go back to stat. Calculate. We think it's linear. I agree. I think it's linear too.
Oh, no. Varse. What's varse do?
Should be varse is like one variable probably.
I don't know. I think there's
Okay. My R is about 9.98, so we're saying about almost 98% of the data. So that's actually a pretty good fit. You guys agree? 98%. So my R is about 0.98%. That means like 98% of my data fits. So my answer is going to be a y equals a 38.6x minus 80.3. Okay. Now, let's think about this before I go on, okay? All right? Before I go on, I want you to use your brains, which you have great brains, you have wonderful brains, okay? Let's think about this. This number, we have to be careful because this number won't work very well for us except for to draw this part of the line. Because this number here says if you have 0 years, you'd have negative buffalo. Does that make sense? It's a good fit, but it does not pertain to here. So it's a good fit from here to about here, right? You guys agree with that?
Yeah.
Okay. So knowing that, it's still part of the equation. We can use it, but we know that if we get down to here, it's not going to work for us. We'd have to use a different equation.
Because we're starting with those 80 buffalo.
Right, exactly. We might be starting with 80 buffalo.
80 buffalo.
Right. That's about it. We started with 80 buffalo, okay? So then put 15 in, predict population 15 years, just put 15 in here. So I'm going to go y is equal to 38.6 times 15 minus 80.3. And then I'm just going to use my calculator. So I'll go 38.6 times 15 minus my 80.3, and I'd have about almost 500. I have about 499 buffalo.
Mr. Davies,
Since
you can't have point something of a buffalo,
you are so smart.
shouldn't we instead
It's a straight buffalo.
So I rounded up.
round?
I think you're so right. I rounded up.
But like, wait, shouldn't we round in the equation as well?
I would like to keep the equation as accurate as I can.
That's still represented for data.
Yeah,
Okay.
yeah. But I think you're asking a marvelous question. I really do.